So the last thing I want to do before we get into numerical solutions, which we will have time to start today, is let's think about an example where the body is, let's say we don't necessarily just want to model the initial part of the response of the system. So what I'm saying is we've said T initial is 300. Let's imagine that there's a scenario where this response that keeps happening repeats itself in time. So from 0 to 0.5 seconds, you see this ambient temperature spike and then return, and there's this like cyclical response. It just keeps doing this. And we want to know what is the like steady state, pseudo steady state behavior of our body that we're trying to model. So we call that as this cyclical steady state. We want to see how this thing will continuously respond in time. So let's look at that example. All right, here's what I mean. So we have, this is our initial condition, or our initial time, and then you have the temperature response. We just saw it does something like this. What if I repeated this over and over? What would it look like? In the end, you'd expect something kind of like this, right, where it's come up to some temperature and it cycles as it follows the ambient condition. But it's not starting at the initial temperature. So how would we model something like this? Well, it turns out it's actually really simple to do this. We have the exact same derivation. All we're going to say is instead of t at x equals 0 equals t initial, right? We're not going to say that, or sorry, not x, t at time equals 0. We're not going to say that. We're going to say instead that t at time equals 0 is equal to t at time equals, we'll call t cycle, where t cycle is the end of this point here. Right? So it's a little bit funny, thinking about how that works, because you're solving this expression to kind of determine that temperature. But analytically or mathematically, it's completely valid to say I need to just force the temperature at the beginning to equal the temperature at the end. Like it's valid to do that. Yeah.
So is T cycle a time or a temperature?
It is a time. Did I write it as a temperature?
Oh,
yeah.
T, okay. T.
Time. Yeah. So it's the time at which this thing would repeat itself. All right. So you're just saying I want those two temperatures to be equal to each other. And then what you're doing is you're actually solving for the value of C1 that makes that happen, right? So if I go through, what you essentially say is that, let's see if I have room down here. So what you're essentially saying is, okay, temperature at time equals 0. If we plug T equals 0 into our temperature equation, we actually get just C1 plus C2, right? That was evaluating this expression here at time equals 0. So left-hand side here equals what? Right-hand side. So that becomes evaluation on the right-hand side is equal to, come on, C1 exponential of minus T cycle over tau, LC, plus C2 plus C3T, T cycle, running out of room, plus C4 T cycle squared plus C5 T cycle cubed. Sorry. What I'm doing is I'm just taking T cycle and plug it in here, and then didn't leave myself enough room. But you have this equation, right? You have the only things involved are C1, which we don't yet know, and then C2, C3, all those we do know. T cycle we know, and tau LC we know. So you can solve this expression for C1, and now you have your new constant. And when you do that, plug it in. Let's look back at ease. So we do that and plug it in. Here was the original initial condition that I had enforced. T initial, sorry, I think this is probably too small. Let me make this a little bigger. So this was from the first time we solved the problem, where we're saying T initial is equal to the expression evaluated at time equals 0, which is C1 plus C2, right? That was the initial one. Now let's comment that out and plug in our new boundary condition, our new initial condition, which is down here. So I'm going to say T cycle is 0.4 seconds. And here's what I just wrote out poorly on the last slide. But it's the same thing, right? It's this cyclic steady state condition. So if we solve this, we should be able to now see my temperature, T at time equals 0, is not the initial temperature. It's something else. This is the temperature that would be repeating at the cyclic steady state. Right? And if I go plot this out, so let's go back to our table, rerun the table, and then look at the plot. This one. Not sure why it's, I went out of bounds. So just imagine that this, now let me do it the right way. So we'll go back and evaluate this from 0.4. And then there, right? So now this is the temperature profile that is going to be occurring. The blue line is going to be occurring in that body infinitely, indefinitely, right? It's just going to repeat. But at this point, we could pin down, like, you want to know what it is at any moment in time. It's not constant, right? It's this cyclical steady state condition where things are still changing with time, but it's repeating itself. Okay. Questions on that? Yeah, Matt.
Can you always choose like T cycle if you go back to the slides?
Yeah.
Like after that first T cycle, it doesn't look like the temperature is ramped up to that final cyclic steady state. So
right. So for the analytical solution, you're solving for it sort of forgets the fact that there isn't any initial condition at all. You're forcing the problem to solve for the value of C1 that's always going to be true, right? So it's just saying that this thing has to repeat itself. If you're doing a numerical solution, which we'll get to, then you always want to start at some known condition, and you might need multiple cycles to come to this cyclical steady state. And that's something that you need to evaluate. And I think we'll see examples of that. Yeah.
How do you know this problem, I guess, was quasi-stable like this? Just because it didn't blow up when you did this?
Well, it has to, so it's always going to be stable in the sense that the body temperature is going to be in the range of the ambient temperature. Right? There's no reason why, we could look at the math here. So there's no reason why you would ever have this term, so C1. So C1 is going to be solved based on the initial condition or the steady state condition. So as long as that's within the range of temperatures here, like there's no reason why it would blow up. You know what I mean? Like there's nothing that's forcing temperature to go outside these bounds. It's always going to be between them. Is that what you're asking, or something different?
I guess, how do you know that it exists, that in this pseudo-steady state that it's going to come to a point where T initial is equal to T end?
Because we're sort of forcing that to be true, right? We're saying, with this equation, we're forcing it to solve for C1 such that this is the case. So my temperature at time equals 0, whatever that is, has to equal the temperature at the end of it. And it solves for the single temperature that allows this to occur, the cyclical steady state to occur, without like violating conservation of energy or anything like that, right? It's achieving that almost magically this way.
Then is there any way to know, I guess, from what we did here, about how long it takes to get to some high percentage of this steady?
Yeah, yep. So if you look at tau LC, that'll tell you kind of the response. So if you see that, okay, I have this cyclical condition, my tau LC is 0.01, right? You're going to see it's following along really closely, but it would sort of, if I could draw here. So let's imagine a case where tau LC is like 0.01, something. It's a really small number, like we saw before. You can still get the cyclical steady state. It's just that it's going to say, okay, it's like this. Right? It's kind of following closely with the peak temperature, but it's lagging a little behind. But it's never quite getting down to that initial condition. So this is going to come to this cyclical steady state pretty much immediately, right? Even before the end of the first cycle. It's forgotten by this point what happened over here. If you have a really long time constant, right, it might do something like this, where it starts off and it's going up, and then it sort of goes down, and then it goes up a little bit more. Right? This really long time constant is an indicator of how long it's going to take to equilibrate. So if it's 10 seconds, you better run 50 of these cycles before you get to that cyclical steady state condition. Yeah, the TLC is really the key to that. Yeah?
So in controls and electronics, generally you'd say like 4 to 5 time constants is really close to steady state. You're within like 5%. Is that a good assumption for long capacitance problems as well?
That's a really good question. I think yes, because what you're trying to do is you're trying to get this exponential term to be pretty small in those cases. And an exponential of -4 or 5 is, by most people's definition, small. If you have an exponential of -1, that's still like 0.3-ish something. So you're still going to have a pretty significant contribution from the initial response, the homogeneous part of the equation. So yeah, I think that's a pretty good rule of thumb. Yeah. Okay. So okay, I mean, it's really not that hard to do these equations. I think the things to notice are, we're doing this with one boundary condition, and why can we get away with that? Because we have a first order derivative, right? We don't have d squared t like we did in the conduction problems. We have a first order derivative, which means we're only going to need one constant or one boundary condition. So the ODEs look a little different. The process is pretty much the same. And then you end up with an analytical solution in time. What you're going to find, though, is I think you can do this for limited circumstances, just like you can for conduction. A lot of times you're going to need to go to numerical models if your conditions are too weird, or you've got a lot of things going on as a function of time. And so what we're going to talk about next is how you start approaching the numerical problems. Okay, so let's see.